Okay, welcome back. And last week, I know there were a lot of students that need to, attend the safety environment something kind of workshop. So there were not many students here. Once again, I would like to welcome you and saying that we will kind of change the course name. All right, and the course name will be classical and statistical thermodynamics. All right, because that's almost 20 years this department teaching this course in this way. Okay, but with the wrong name, I will say. So if this is not suitable for your requirements, you feel free to, quit this course because there are plenty of students in this classroom, about more than 100. Although it doesn't look like 100 students here. Right, so plenty of students here. So you feel free to study at your home by using the streaming Microsoft Teams, or you can just stay home for watching the YouTube that I will always upload my course, okay? And also if you don't like live version, you feel free to watch 2024 version, okay, last year. So in my YouTube channel, you can always find a lot of course or research knowledge share resources. So feel free to subscribe and push like, and then you can I guess that's all my stuff, all my working and research experience, knowledge that share there. All right, I guess it's okay. Thank you. Oh, she's the teaching assistant, Li Jun, and then this is her email. Oh, by the way, please make sure that you join Facebook club. Okay, you can search like NYCU MSE 2025 Thermodynamics of Solids. So you can search that and you can request to join the Facebook club. This is really important, okay? So because we will upload a lot of resources of this course, including the YouTube movie. Okay, so I guess that's it. Okay, another thing is that today is quite, I have very tight schedule today. I need to attend a conference in the afternoon, so my high speed rail is at 8 past 12. Okay, 12:08分. So I need to stop this course around 11:30. All right, so which means that I will, I should, I don't need to break, okay? But you feel free to go out, okay? Feel free to go out to have breakfast or to eat what your breakfast or something, okay? 听得懂吗？我12:08要去赶高铁，8分的高铁，所以我11:30就必须要离开。那但是因为这样，我就欠各位30分钟嘛，哈，对，所以30分钟我就用下课来补，正好就是30分钟，对不对？20跟10 minutes for the break。但是我知道大家一定会觉得哦，好累，我更累哈。不过没关系，请大家想出去就出去，想回家就回家，想睡觉就睡觉，这样这样好不太好。总之就是你想做什么就做什么，好，然后你想出去就出去。那想吃饭就吃，这边可能不能吃啊，哈，出去就吃饭也没关系，哈，我完全不会介意，啊，完全不会介意，我不会，反正这是各位的事情嘛，对不对？哈，但是很不好意思啊，哈，因为下课当然是需要，这大家可能需要休息或什么的，所以如果你今天觉得下课那一段时间 那个比较就是想要出去，但是又怕 miss 掉我的课程的话，没有关系，我有 YouTube，OK，我今天就会上，这今明2天就会上传，好吗？所以说你不用太担心，想离开就离开啊，反正我全部都录下来了，OK。如果真的看不懂，你也可以有2024年的，OK。Oh, another thing is that I have a chat box, chat GPT. This chat GPT is different from what you use normally, okay? Because I ask teaching assistant to upload my handwriting, PDF, handouts, and also textbook, and also some solution of the examples. All right. So we have tailored Chat GPT, and I shared it in Facebook. Okay, so Facebook Club. So please feel free to use that link and ask the question about this course. All right. Well, please don't ask about the teaching assistant or grading or something. This is a little bit because what I upload is from the handout in the past few years. So teaching assistant information may not correct. OK， 听得懂吗？我为了大家做了一个跟一般 ChatGPT 不一样的TA 助教啊，电脑助教。这个助教是因为我有上传我过去几年的讲义跟课本的资料啊，还有 solution 解答等等的。所以说他会回答你依照这样子的，就是在这个课程，所以跟一般的 ChatGPT 不一样哦，它是有依据的来告诉你，甚至它会告诉你讲义的哪几页 ，OK？ 所以这是我认为还不错的地方。但那大家要怎么样拿到那个连接呢？要到 Facebook Club，OK？、And also I encourage you to submit your questionnaire about this ChatGPT bot, okay? And also in the Facebook club, please upload your opinion about how it is, okay? If this ChatGPT answer your question incorrectly, you need to rate that 1 star or 0 star, or I don't know. Just give the comments, okay? I will note that and I will try to retrain it, okay? I will try to modify it. So this is a procedure that make this teaching assistant, I mean, ChatGPT teaching assistant better and better, all right? So please ask all the question to teaching ChatGPT first, and then ask the teaching assistant, and then ask me, all right? Good. Right, so let's continue our lecture. Last time, we talked about how important of thermodynamics, and also introduce several terminology like system wall, process, and quasi-static processes. Okay, and units, logic, equation of state, blah, 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 and how to get the 0 K and the gas constant, right? Okay, now let's continue. Let's continue our lecture. All right, so next, so we all know PV equal to MRT, right? But the great van der Waals scientists say that actually this is not really correct, all right? Because they found that the PV equal to MRT cannot describe some process. For example, this process, okay? If you have container, if you have gas inside the container, you has a piston and to press, and you will find that in a certain procedure stage, it will become some liquid and volume, I mean gas coexist. All right, so you can see that liquid and vapor equilibrium stage. All right, so it found that van der Waals found that this PV equal to MRT cannot describe these things. So it mentioned that okay, it should consider two more important factors that previously PV equals MRT did not included or taken into account. The first thing is this is intermolecular interaction. All right. So previously we just treat that all the gas atoms in the container cannot see each other. Okay, cannot see each other. They will penetrate each other. Okay, they are all invisible to others. Okay, so they just do what they want. Okay, but actually this is not correct, right? Actually, they has some interaction. They may bump together. They may attract or repulsion. So actually, this is more complicated behavior going on in the container. So they say, okay, they should have interaction between atoms. So the pressure turns must adding some extra term. All right, to encounter. So you can see that previously it doesn't consider any interaction. So pressure is something you know, but all the atoms should bump together. So they have more pressure between them. Okay, so this should be added in the term. And then we also previously it also said the atoms are infinitely small. They don't have volume, they don't have size in the container. So, which means that the volume of the gas is totally equal the container size, V. But actually, all the atom has volume, right? So it should be molecular size, molecular volume. So the gas container volume should be minus all the atoms volumes. So it should be the actual free space, right? So after the van der Waals comes up this equation, we found that this is actually third order polynomial. All right. So which means that this is it's not a second order. It's not the first order. It's the third. So it should be kind of wiggle curves, right? And it is very good to describing this kind of lines. OK， 好，我们要讲的就是之前我们讲 PV equals MRT 嘛，哈，那但是它有很多假设，例如说它是假设每个气体的原子是或分子是不会互相碰撞，没有任何的交互作用，甚至它没有占据体积，它不会看到彼此。那所以说它的 PV equals MRT 的这样子的描述是无法描述很多现实生活中的气体的行为，尤其是这个气意象的行为。那凡德瓦就发现这件事情，他就说：“哦，那我必须要去考虑每个原子之间的交互作用跟它自己本身的 size。”OK， 那我们可以想象，原本他们假设没有看到彼此，它有一个 P 是 pressure 嘛，但实际上他们会互相碰撞啊，互相吸引啊，所以它更多的力在里面，要把它加上去。那另外一个 V 是原本是 container， 它是空的嘛，哈。那它假设 atom 都没有体积，那它当然就是全部的 container 的这容器的体积嘛。但是实际上分子也是有体积嘛，也要把它减掉啊，对不对？好，所以这边有个减。好，那我们发现这3次的曲线很适合去描写更复杂的行为。Alright, so next we'll talk about PV diagram for carbon dioxide, just an example. Alright. So previously, the PV equals MRT should looks like the curve should looks like something like this. All right. So something look like this. So if you have P in y-axis, x is v-axis. Okay. You have this kind of curve, but real isosome. We also call this isosome. All right. Real isosomes, which call the 温线. So you can imagine that this curve is called isosome because the temperature and N and R are all fixed, right? So the right-hand side should be a constant, okay? So the PV curve here is called isosome because the temperature is fixed, all right? But in the real world, the real isosome looks like this. As we mentioned in the previous page, you see there is a platform here, right? It is actually liquid gas coexist region, and we can pinpoint the starting and ending points of the platform, and then we can draw a line saying that, okay, this is liquid and gas. Liquid and gas coexistence curve. Okay. Oh, by the way, I should explain the figure first. You see there's a P here, right? There's a pressure, no problem. But there's a V bar, okay? And there is a L. This is a unit, okay? This is a unit with this is unit L times mole minus 1. So you can see that this V bar is actually in our course symbol. It should looks like small v, which means that it divide the mole, kilomole or mole, and it becomes specific value. Okay, it becomes specific value. So I know this figure is not compatible with the textbook figure and textbook symbol. Now I give you a translation. All right, this V bar actually small v, okay, in our textbook. All right, so you can see this. When you have different temperature, you will have different curve. All right, different curve. And we found that there is a platform, and PV equal to MRT cannot looks like this. Okay, cannot do that. But van der Waals equation could do that because it's a third order polynomial, and it can be derived like this. If you expand it, and it looks like here like an ugly term. All right, and if you plot it, you will looks like this. You will have a result like this. Interestingly, it has a down and up curve. It's really interesting. We said that it should be explain this, right? It should has a platform, but why you looks like a valley and hill? Why? Actually, there's a good way to make it interpretable for this, explainable for this. There is a smart scientist called Maxwell. Well, it said actually all we need to do is find a line that make the hill and valley area the same. Okay, the same. And then we can find that straight line just and fit to the left-hand side figure. Okay, Maxwell equal area construction. Okay, what does that mean? Okay, what he said is that Maxwell said here is the release, the work, and here is work done on the system. Okay, so you can see that when it do the pressure, change the pressure, maybe increase the pressure just like this. Okay, just like this, and it increase the pressure and increase the pressure, and then you can imagine that in the real world, if you press that, you give the work, you work down on the system obtain the work, and then it suddenly used those work to reduce this work to phase change. Okay, so you can see that it is small atom obtain the work and then do the phase transition. So actually it is like this: obtain work, release the work, obtain work, release the work. So it looks like a straight line, but in the theoretical calculation, we treat this system as a whole. Remember that classical thermodynamics treat the material as a whole. So everything just have one step: obtain the work and reduce the work. So there are actually thousands or maybe million, billion, like hill, valley in this straight line. But because the limitation of the theory, we only have one shot: work and release. That's it. So that's the reason why we need to find the equal area. So all the work done on the system used to phase transition. Okay, so we just find the equal area and write the platform, and we can have a proper line and comparable to the experiment results. All right, so I think that's van der Waals equations quite and Maxwell are quite genius. All right， 好，这边很快速的讲一下，就等温线 PVD equal to MRT 的线会长这个样子。那但是事实上它是长这个样子的。那我们说这个平坦的线就是 liquid gas coexist， 就是液体气体共存的区域 ，OK。然后我们这边特别讲到一下，这张图是从别的课本拿来的，所以它们的符号不太一样。那这边的 V bar， 我们可以看到后面的叫什么单位是体积的单位除以摩尔 ，OK， 质量的单位。所以其实这是我们在课本上的小 v 的意思，因为我们已经把它除成比的体积了哈，比的体积这前面都有讲。如果你听不懂的话，你可以去看我们上一次的 video。那然后呢，所以我们就发现这个绝对无法显示这种形状嘛。但凡德瓦的 equation 是可以的哦，很厉害哦。它是一个三次的多项式，它画出来是长这样，有一个凹槽跟一个上坡。那我们就觉得，不是说可以去比较吗？对，要再加一个东西叫做 Maxwell equal area， 叫做马克斯韦尔一样大的面积的操作啊，就是说他把这边这个上下找一条线，而这条线正好可以把下面的面积跟上面面积是一模一样的话， 你就找到那条线。好，这条线呢，为什么呢？我们来解释一下。我们说，真实的状况来讲，你给它压力嘛，然后它给它压力就会有给它 work， 你给它 work 功，这功它就会把它拿来相变化嘛，对哈。但是有很多个 atom 在里面，很多的原子在里面，所以你一给我能量，我就拿去用去做相变化，所以它实际上是凸起又降下来，凸起又降下来，所以它就是拿到能量就用了，拿到能量就用，拿到能量就用，所以对，它其实是很多个上下组成的这个直线。但是我们讲过，传统热力学我们都叙述一个材料是一个全体啊。所以说它不会有那种拿到就用，拿到就用，它是拿到全满才用。好，这是数学理论的一个限制。OK， 那所以说你就找到就是说全部等于是先聚集所有的能量以后再一次把它用掉这种感觉。当然这是不真实，但是我们可以用 Maxwell 这个提出来的方法去找到这条线啊，然后我们就发现，哎，这条线可以跟实验就是非常的契合，还蛮天才的。OK, right, so that's introduction. So let's move into the next review. Again, I would like to say this course is actually classical and statistical thermodynamics. All right, so which means that we will have 3 or 4 weeks to review classical thermodynamics. Maybe most of you has done that before, okay? Because most of you are graduated from material science engineering department, but some of you may from mechanics, civil engineering, or bio, yeah. So maybe you are not that familiar with classical thermodynamics. So that's the purpose, that to allow you to review that and connect well to the other important course in Department of Material Science, all right, in the master and PhD program. All right, so maybe you think, I have known that. Yes, I know, I understand. But okay, something is a little bit different from class previously what you learned, because in this course, statistical, right? Statistical thermodynamics, which means that you have a lot of chance to use math, okay, calculus. All right, so you will see a lot of equation and math. I have heard that this course, some students, your seniors, told me that my course are always the most difficult one in this department because it involves a lot of math. All right, so be prepared to face a lot of math. All right, I know this is difficult, but well, you are a master and PhD student, right? You can do that. Okay, so let's very quick. We'll introduce the zero law. I guess that's really easy, right? If you have 2 systems separately, thermal equilibrium, and which means that they are all thermal equivalent to each other. Too easy. Let's go. The first law is that the first law is quite important, right? So the heat supply is equal to the increase in the internal energy, okay, of the system plus the work done by the system. Energy is also important. Conserved. If heat is taken into account. All right. So which means that energy is always be there. It never decrease. Okay. So in most case, okay. So the bar Q is heat, and you notice that there's a bar here. I will introduce that later, explain later. Internal energy. Well, you can see D bar and D is are different, right? But you know D is kind of change, right? Change of the internal energy. And D bar, W. D bar also means change, but we will introduce in more detail later. All right, too easy, right? 就是第一定律就是你只要给它热，它就会理论上呢就会加在这个系统上，变成它的内能，或是让它用这个热去做一些事情，例如说相转变，例如说改变它的体积，等等等等等。OK， 好，就这样。So let's introduce this one by one. All right. 哇，好累哦。对，我可以聊聊天。就是上一次我讲到，就是我喜欢看动漫跟漫画啊等等的，然后就有聊到一些，就是就是我以前曾经推荐给大家的推荐给大家看什么东西这样。结果啊，就是我通常都还蛮早开始看，就是以后会很火红的漫画这样子。就例如说，讲了就开始泄露年龄了啊，就例如说《进击的巨人》啊，就是很早很早我就开始看了，然后还有什么《一拳超人》，我也很早很早很早就看了，前几集我就看了，然后还有什么路人灵异100%那个100路人100那个，我也很早很早就看了啊，还有什么？对，所以我还蛮就是我觉得我常常会看一些我觉得很好看的东西，然后到最后就会很火红，这样还蛮不错的。结果最近我竟然发现有一个我 lag 很久很久的好漫画，我竟然没有看，叫做《王者天下》，有看过吗？《王者天下》已经出了17年了，所以好像跟大家其实年龄差不多。有看过有听过这个东西吗？《王者天下》，我觉得超好看的，但是我是最近才开始看的。而且他已经出了那么久了，我以前都觉得这什么东西什么东西，但是最近看我觉得哦超好看。他在讲以前战国时代，什么秦始皇要要统一中华的事情，然后然后我看了我就觉得这个作者未免也太厉害了，它里面有很多种类的故事，就例如说战争的故事，例如说打架的故事，热血打架的故事，然后或者是文戏，就是文官在那边吵架啊，什么什么那种辩论故事。我觉得他每一个都做得很好，所以他的画，他每个画都让我觉得很精彩。因为有些漫画就是很适合文戏，有些很适合打戏，对不对？有些是很适合画战争的，这样哦，他全部都画得很好，每一个地方都让我觉得好好看哦。然后我觉得还蛮有趣的事情就是，我以前小时候啊，我不知道大家有没有这种感觉，在小时候看那种《三国演义》呀，或者是就是一些历史故事的时候，你都会觉得说这些君王怎么那么笨，或者这些将领怎么那么笨，就是你不就这样就好了吗？然后就是我都觉得说，如果今天是我小时候啦，我就觉得是我去带领他们的话，我一定统一中国，这种感觉，这种感觉。但我现在看到那本漫画，然后我又仔细的去想一下我现在的状况，我就觉得他们那些以前的将领都超神你要想想看哦，我现在带一个20几个人的实验室，我会觉得哦焦头烂额，哦好难哦。但是你看以前那个将军，他要带几千几万人然后去打仗，然后而且那些兵啊你要想想看，一定都没有各位聪明，一定都是就是很久很久以前的那种啊，没事就被抓过来征兵的那种人，所以你要控制这些人。然后去做出一些精密的战略，我觉得这是非常非常难的事情所以然后或者是说一个国家，然后要去统治国家，你看现在的现在当总统也很辛苦，所以我就觉得哇，以前的人其实是很难很厉害的。那我以前小时候就不知道这些事情，然后还看清那些国王啊或者将领之类的，所以现在发现哦，其实会在历史上留名的人，应该都不是泛之辈这样。好，这是我的一个建议，就是想法这样。那我可以介绍给大家就是《王者天下》，而且我发现了他已经出了4部电影了。通常这种出电影表示很红啊，然后他也出了4部那表示说我 lag 了多久？然后这个让我觉得有点就是我竟然没有跟上这一波这样。 好，总之推荐给大家，好，还蛮好看的。Alright，然后我还跟大家讲说，如果各位有好看漫画，一定要推荐给我，好不好？可以在 Facebook 上留言或者是私讯我都没问题。漫画实在是对我来讲太重要了。OK， should I translate what I said? I was just saying that there's a comic book called Kingdom. 好，我还特地去查哈，Kingdom. It's a comic book. It's a Japanese manga. All right. So I recommend you to see that. This is quite nice, and it's about fighting and war and countries and kingdoms. Quite good. All right. I recommend you to do that. To read that. All right. Let's go back to the work. Yeah, work. D bar Q equal to du plus D bar W. Okay, the work done by an external force on a gas enclosed within a cylinder fitted with a piston. Basically, I'm saying this. Okay, and then you have force on it. The force equal to P times A. What does that mean? Force is actually Newton, right? Newton. The unit is Newton. The P here, you know that Newton per meter square, all right? And A is meter square. So you can see that, yes, when they P times A times together become F. All right, so the D bar W is actually the force times the distance it acting on. Okay, so force times distance is the work. I guess you learned that in senior high school, junior high school, I don't remember. So your force, your work, your change of work is your force times the changing of length. And also your F become PA, so A times dx is volume change. All right, so it's quite nice, nicely done, nicely connected, and also apply to any shape. So if you just, this is one dimensional, one direction. However, if you have multiple direction, which means that you need to integrate all the change. So you need to integrate that dV, and because the volume is actually from volume A to volume B. So, and also you assume that the pressure is constant. And if you have constant, you just leave out, take the P out of the integration. So it becomes P times volume change. Okay. And also we have the sign convention. Sign convention is in this equation when you work down on the system or down by the system, you will have different sign. All right. So, and this sign convention is actually set by the textbook. All right. So there's no reason. I'm sorry. So work down on the system, volume decrease, right? You press that, which means that your D bar W become less than 0. By contrast, D bar W greater than 0, which means that you work down by the system. So your volume increase. So you kind of push your, make the volume increase. So your work done by the system, your system do some work. OK， 好，很快速的讲一下功哦，这个功其实就是我们高中的时候学到的力乘上它的距离，就是它做的功，对不对哈？那我们就拿这张图来当例子，原本里面有一个 gas， 然后你有 force 压下去，力压下去，走了 dx， 那这个系统它改变的功就是你的 F 乘上 dx。那我们的 F 又可以写成压力乘上面积，为什么呢？你可以看到这个压力的单位跟面积的单位乘在一起就是牛顿嘛，哈。那所以我们的 F 就变成 PA， 然后 A 乘上 dx 就变成 dV， 那就是体积的变化量乘上它的压力咯。那这是 一个方向的。但如果你今天有好多方向的话，你就要去做积分。那如果是做积分的话，我们假设我们的 P 在这个 P 为不变的状况下的话，我们可以把 P 抬到外面去，积分外面去，然后就可以变成 P 乘上两个体积的差别。好，然后这个 sign convention 其实就是正负号的规则哦，是规则，所以表示说课本跟学科之间可能会有不同哦，哈。那我们这边就是说，如果是 d bar 打 w 等小于0的时候，它是 work 做在这个系统上。那如果今天它是大于0的话，就是这个系统去把消耗它的去做别的功就对了。OK， right. So you can see that this work is actually related to pressure and volume. Okay, so typically, we will make or treat the work is a function of P and V. Although I know that the maybe your P and V related to temperature or something, so also make the W related to temperature. Yes, we know that, but the most straightforward, most straightforward function is work is determined by pressure and volume. Okay, you can use other variables. It's okay, but more straightforward. When you do the experiment, you will use P and V to measure the work. All right. 好，我这边刚英文没有讲哈，所以我现在没有翻译。好，这 W 这意思，这边 W 就是 work 嘛。那我们可以看到 work 就是跟 P 跟 V 有关，你改变 P 改变 V 就会影响 W。那我们就会说，我们通常都在实验的角度也是来讲也是，就是我们常常都会使用 P 跟 V 当做是 W 的变数，我们改变 P 改变 V 看它的 work。我们当然也可以说啊，这个 V 可能跟 temperature 有关啊，所以说这边也可以说 W 是 T 的函式啊，可以，但是我就说更 straightforward， 就是第一层的关系就是 P 跟 V，OK， 那你当然可以换变数，这是没有问题的啊，这绝对没有问题，只是我们最直接的做实验就是想说，哦，我要去看 W 的改变，我就去改变它的 P， 改变它的 V， 哦，这是很正常的直觉哦，那最常见就是这样。All right, next. We have various examples of work. Basically, when we learn thermodynamics, classical thermodynamics, actually it's kind of 19th century things. It's really old. It's really, really old. So we are now, 2025. We are advanced. We have technology, advanced technology. Why we should learn that? Why we should learn P and DV or something like that? Actually, this is just the starting point. Okay, starting point. Actually, it's just an example to let you know how the material, how the matter in this world behave. All right. So you can see that when we talk about film and cell or magnetic material, dielectric material, they are all small material that very advanced material used nowadays, right? But when you learn gas, you will understand why the setting of all this system, they have exactly the same setting. You see, they have the intensive variable, and extensive variable, surface tension, area, and film. These two things times together become the work can be, relate to the film. Or you can say magnetic material, okay, magnetic field and magnetization, M. So these two things can be related to the work done by the magnetic material, or dielectric, electric field, and polarization, EDP. So actually, you see, they are really similar. They are in very the same form. All right. So when you know how to do this, you can kind of elaborate or apply to the material that your lab focused on. All right. So for example, if we, all right, and now we are going to describe why there is a dbar W. Dbar means differential of W is inexact. Inexact, what does that mean? Which means that it depends on path. Depends on path. So inexact has the bar here. The W depends on the path. All right. So you can see that PV, right? So your PA point, initial point, this final point. If you go here, you need the energy here. But if you go from here to here, you has energy here. So which means that you have an energy loss. Energy loss during energy loss. During this process, you will have energy loss. So you see, close integration is not zero. Close integration. So if you from A to B and then go to B and A, you have different paths, which means that this cycle give you an energy loss in this process. So, but if you are talk about internal energy has no bar, right? Du. This is not depending on path. So stay. I mean U. Okay, U here and U here. Well, if you go back to the same region, the same point, the U will always the same, no matter how you go. All right. 好，这边要讲就是很多个 example， 很多个例子，公的例子。我们常常在讲为什么要学这个19世纪、20世纪很久以前、几百年前的古典热力学？为什么？原因是然后学那 gas 为什么？哎，那只是一个例子而已。当时用这个东西给做例子，然后我们会发现，他们的式子跟现代的材料的东西其实是一模一样的。你可以这样子同样的设计，那你可以看到 PdV 嘛，这很正常。那其实你们各实验室，我常常都会看到有二维材料电池的材料磁性材料、介电材料等等的，这些的功不是 PdV， 但是都会有一样的形式哦，它都会有，例如说这什么磁场跟它的磁化量，那你改变它的磁化量是要加磁场嘛，对不对？那不就是改变它的磁化量加这个磁场，那不就是 PdV 的概念吗？所以其实所有的东西材料，世界上的材料或系统，基本上都是符合，就是我们以前的热力学定律，然后我们的定律就会用教学了在第一个例子，那就是 gas、liquid，OK，然后 solid 这种相变化，其实例如说 dielectric material 也会有相变化，只是更复杂而已。例如说 Martin-Stickis transformation， 对不对？所以说这些都可以跟这边是一一对应的。你会了 gas、liquid、solid， 你就会你可能要稍微跳一下，或者你在看书的时候就会原来它是用同样的逻辑再去看待这样的资料，这样的材料。OK， 那接下来我要解释的就是 differential inexact， 什么意思呢？就那个底坝就是 inexact differentiation，这中文我不知道怎么翻译，总之就是它跟它的路径是有关系的。像你从 A 状态跑到 B 状态去，然后再从 B 状态跑到 A 状态去，如果是在内能方面来看的话，这个 A 是完全没有改变的，完全没有改变，因为它就是那样子的状态，内能是没问题的。可是呢，你在过程中你可能会消耗不同的路径，你可能会消耗很多，就是消耗一些能量，就这个图的围起来的面积就是你 energy loss。那可能同学就会说，为什么不走原本的路？很难有的时候是很难的一件事情，你无法控制，你无法控制，它就会有比较喜欢的路要走，那材料就会有喜欢路要走，尤其是例如说像微结构有些从过去以后 你要跑回来，它就不会从原来的路跑回来嘛，这是不可能，太难了哈。那所以说你从别的路跑回来的时候，你一定会有一些 energy dissipation、energy loss， 能量耗损。OK， 所以 close integration 就是头跟尾是一样的积分，不对，对，一样的积分的时候，它不一定是为零。OK， 哦，然后现在已经50分了，所以大家可以下课。那我说过今天是，不好意思，我要30分钟提前下课，所以我不会休息，大家可以随意出去哈。那我也来喝口水，你们可以趁现在赶快想尿尿啊，你都可以出去哈。好，没事。Feel free，我不会觉得，我不会介意啊，只要安静就好。好。I just saying that you can feel free to go out and drink or go to bathroom. Right. 好，等一下哦。一起。Yes. Barrel. Okay. Right. So let's continue. I will give you an example. It's okay. Go. Okay. I will give you an example that ferroelectric material. Ferroelectric material is actually what I learned in my PhD stage. I focus on barrier titanate or PZT. All right, and this is not gas, right? So this is advanced. Sort of advanced at that time. I noticed that this material is really interesting, that it has spontaneous polarization, okay, and reorientation of the polarization. So you can see that actually a material may have different polarization, okay, and if you have electric field, every polarization will go to the same direction, okay. And also it changed the microstructure. So we found that in the material, if you get the electric field, for example, in this direction, it will previously it may go down or go oblique, but after the electric field, it will go to up, follow the direction. Okay, and if you reverse it, it will make all the polarization go downward. So it will have something like this: go up, go down, go up, go down, and this is electric field and polarization plot. So you see, this is exactly just like a PMV diagram, okay, in gas. And then we found that if you give the electric field and positive and negative, you will have different polarization and you will have energy loss. All right. So this is kind of the example that when you done the work, you may have path dependent effect and you will have energy loss. All right. So I will say, yeah, this region is the energy you loss. 好，这边我要讲的就是我大博士的时候，我在做铁电材料的研究。那时候我们就发现这个材料，不是我们发现啊，文献中发现这个材料很有趣，它会有自发性的极化量在这个材料里面。这个其实自发性材料就是每一个点它可能会有往左边的极化，往右边的极化，往下面的极化啊，这样啊，很多极化量。那它还有一个的特性就是，如果你全部加一个电场的话，大家都会随着那个电场变化，然后就一起跟那个电场排列，这样。那所以你就可以往上加电场，然后就变成全部大家都会往上。那如果你往下的话，全部都会往下。所以这造成一件事情，就是如果你今天画一张图 ，E 跟 P 的图，它就会加到正的地方，它就会跑到全部都是正，然后加到负的 大家都会往下跑，就是极化量就往下跑，就会变耗这样，所以它可以变成记忆体。好，然后总之就是这样子跑来跑去，跑来跑去。那这张图就会发现，哎，这就是功啊，不是又是我们之前的 E 底 P 吗 ？P 底 V， 这个 P 是 polarization 啊 ，E 底 P， 这个 P 跟这个 P 不一样哦，你有发现吗？啊，这个 P 我故意写不一样的符号啊，一个是 polarization， 一个是 pressure。好，那你不觉得这长得就是几乎就是一样的东西吗？功就是这样出来的嘛。好，那所以它的步骤就会中间就会出现一个图形，这个图形的面积就是它的 energy loss。OK， 那这个 energy loss 跑到哪里去啊？你猜啊？它一定就是拿来移动它的微结构嘛，对不对哈？所以说，当各位开始在学习微结构的变化啊什么的时候，我们就可以考虑到，就是这些 energy loss 跑到哪里去了？当然会跑到热里面去，它可能会有一些热消散等等，但是大部分的就会把它用来去移动它的微结构的，例如说 grand boundary 或 twin boundary，都需要这些能量去移动它。OK， 所以这有点等于是说，热力学告诉你大概，那你你就到时候越研读越深，你就会发现其实这些能量都是拿来用来干嘛啊？就是用来你常常听到的一些paper 里面写的东西。All right, next internal energy。我知道，就是其实我也不太喜欢在这一间因为这一间实在太舒服了。我自己以前曾经也不是以前我之前也是有那个讲者来这边讲，我们邀请讲者来这边讲分享，然后我坐在下面，然后我是老师，我不能睡觉，然后但是真的很想睡，没关系没关系，我不在意但是只要不要讲话就好了，大家都表现很好了。就是我发现很有趣就是近年来台下讲话的学生比以前多当然你不会你们很棒但我会发现可能是大学部吧就是以前我上台讲话，大家应该就会自动就是小声了就不讲话。一开始的时候，但是很有趣最近2、3年，我发现上台讲话，他们还是继续讲。对，然后想说都已经讲5分钟、10分钟了，他还是继续讲，这让我觉得有点奇怪。就是所以以前小学、中学、高中的时候，他们都这样吗？蛮讶异，蛮讶异，我不知道。不过现在自己有小孩子嘛，对不对然后我自己有小孩子，我有2个小孩子，一个6岁，一个3岁。然后我就在想，我要怎么样去对待他们？就是我有被要求说不能打小孩。虽然我小时候也是被打，大家小时候有被打吗？有点头，然后只有一个点头，有被打这样讲好不太好，算了不要这样调查好了。真的好，所以大家都很幸福，好，那很棒。我以前小时候也是被打上来的，然后我想说，对我到底要不要再这样对待我小孩呢？然后当然了，我没有打他，我都没有打，但是我会骂他，我很凶，但是还是有网络上的人，或是反正就有很多那种教你怎么样教小孩那种，就说你不能打骂你会怎样怎样这样。好了，我就觉得怎么办我该怎么办？所以其实当父母也是蛮焦虑的，就是不知道该怎么做。就是可是如果今天我的小孩在上课的时候跟老师一起讲，我真的一定会骂死他。好，总之，对，但是我不会这样骂同学啦。我知道，不好意思你要安静。但是我是我小孩，我就暴骂。好了，anyway，哎，OK，next internal energy。要不要翻译刚刚的东西啊？好难It's really difficult to be a parent nowadays. OK， 结束。internal energy du 哈 du， experimental fact shows that work done in an anyway 好算了，这没什么 ，just read that and du is negative of the adiabatic work done by the system. Done by the system. Why? Adiabatic means there's no heat transfer, right? So d bar Q will be 0. So your du equal to minus d bar W. Very straightforward, right? Negative of the adiabatic work. Okay, internal energy is the total energy contained by a thermodynamic system. It's the system, it's the energy needed to create that system. Okay, so which means that if you are there, if the material is there, there must some internal energy inside, okay, in that. And you can use a lot of treatment to make it increase or decrease, all right? And internal energy is some sort of like the status of the material, okay? The status. So one status, two status, no matter how you go, how the path, how you go to the next step, next status, their internal energy, well, in this point, they will be all the same, no matter how your path it is, all right? Just internal energy is kind of describing the state of that material at that moment, all right? Right, so the internal energy is so important. State variable, state function, state function. Or you can say state variable when you, well, function is changing, right? Variable is okay. Well, state variable, state function, which is independent of the path. So which means that if you go to the other place and then go back, you have a closed loop. You will have zero closed loop integration. And also, it is nature to choose V and T as a function of the U. So as you can see that if you have container, and you have piston, all right, and okay, and so how you describe the internal energy? Basically, you change the V and change the T. So you can see that if you heat up, you must give the, you must change in its internal energy because you give the energy, right? So you have V plan, T plan. So it's nature to choose V and T to describe the function of U. 不好意思啊，签个名。OK， 好，谢谢。Right， that's it。好，我们要讲的是内能。好，这内能的话，它就是来叙述一个材料它在现在这个状况。好，它为什么会出现在这里？它一定要有这些能量，它才会出现在这里。OK， 有点像是它本质就是有这么多能量啊，你我都是能量啊，那都有能量在身体里面这样。那当然在这个系统里面，如果你今天在一个绝热的状态，然后对，等于是说底坝 Q 等于0嘛，对不对？好，那这样子当然就可以是说你改变的 内能的改变，当然就是你负的功的改变。OK， 其实也就是很简单啊，就是例如说你今天没有吃东西，然后你也旁边也没有热转换，然后你不吃东西，你去做一些功，也当然会消耗你自己的能量啊，大概是这样。好，那好，然后它是 stable function，stable function 什么意思呢？就是跟你的路径没有关系，就是说我刚刚讲。功的改变啊，功的体积改变，还有你直接给它加热也会改变啊，所以通常我们就会以体积跟温度当做是它的函式，好，我们会利用 V 跟 T 去改变它，去看它的内能。但当然还是一句老话，你也可以把它改成 P 啊，你也可以改成别的都可以哈，都没有问题。但是最直觉的啊就是 V 跟 T。OK，next heat debug Q。Debug Q also really similar to debug W, all right? Very similar. Because if you go, as you can see, U is a state variable. So if you go to other place and then go back, the U will always the same. So debug, the U will be 0. So which means that for a cyclic process, debug Q is actually debug W. Actually, they are the same form. Okay, so you can see heat and work are equivalent of changing in internal energy. So you can see that you either give me heat to change the internal energy, or you can give me work to change my internal energy. So basically, for internal energy, these two things are the same. All right, and also I would like to give you a really important sign convention here because in this textbook, debug QW, debug Q debug Q greater than 0 is out of system. Okay, and completely inverse case. But well, both are correct. Both are correct. Just the sign convention. Okay, so if you are from chemistry, please be careful about this. All right. 好，我要讲中文了，就是热嘛，热跟功其实是对于 internal energy 来讲，其实没差的。好，因为你看它就是等号左边跟右边嘛，哈。然后如果你今天是做一个close loop，就是初始状态跟结束状态是一样的时候，内能是不变的。那就表示说 debug Q 跟 debug W 其实根本就是一个同样的东西呀，哈，它是等效的。那这边有一个很重要的东西叫做 sign convention，就是正负号的定义。在我们课本里面，我们说 debug QW 的话，大于零的话 ，debug Q 大于零的话，它是热流进系统，然后反之是 out of， 就是流出。那这跟化学系、硬化系我听说的好像是不一样的哦。他们好像是说 debug QW 是 out of system。那两者都对哦，两者都对，纯粹只是计算方式的不同，或是你反正只要统一就对了。OK， 所以你要小心啊，如果你是从化学系来的，或者是硬化系来的，这边要小心啊哈。那请到这边的，在这边的时候记得要改一下这样子。All right, so let's go. Math is coming, math is coming. All right, be careful. 数学来啦哈，加油啊！从这一章开始，这一页开始，就会发现哦，好多数学。From this page on, you will find a lot of mathematics. All right. Okay. Go. Some calculation of work. Okay. Debug W equal to debug Q minus du. You know that, right? Okay. So let's start. We know that the bar W can be written by P dV equal to d bar Q minus du. Right. So, oh, by the way, if I made a mistake here, you can raise your hand and let me know, and you will have bonus. OK？ 如果今天我写错的话，你发现了你就举手告诉我，然后你就会有加分哦。OK？ 好。而且很奇怪，就是我已经13年了，我每一次都还是会有错误，我也不知道为什么。即使是我小抄，我的小抄非常的精美，我小抄非常的精美哦，会跟这个一模一样，所以实际上我那边念的很，我在那边念的很头头是道，但实际上我纯粹只在念小抄而已啊。那对啊，所以说如果今天还是有错误的话，请大家提醒我。All right, just saying that this is really difficult. It's impossible that human being has no mistake, right? It's never perfect. Even I taught this course for 13 years. Every time I still make a mistake and then attention. All right, let's go. So for a reversible process, the bar W equal to PdV. Okay, so that's how we obtain this, right? Now let's let V equal to VT comma P. What does that mean? Which means that we treat the V is a function of temperature and pressure. Okay, so what does that mean? What does that mean? Function of temperature or pressure, which means that the volume change has two contributions. The first one contribution is from changing of T. The other is changing from P, and you need to sum them up together to get the total change of V. 不要这样吧。嘿，这样太不好了吧？这样谁打电话给我，你们都看得到。好，这个药妆是慢性病的药了，好，他提醒我去，那个去拿药这样。嘿，这样不好呗？能不能不要让它联动啊？有人会这样，有人会设定我